We'll talk about that in a second. Anybody else for the quiz? All right, because this quiz was somewhat short, I will just go over it real quick. So this was actually problem number... It's problem number 31, but I use sines instead of tangents. So the problem in the book is tangent of e to the x plus e to the tangent x. So derivative here, on this first one, you have sine of e to the x. So the first thing you have to do is take derivative of sine, which is cosine of what's there. Then times chain rule, the derivative of what was inside. The derivative of e to the x is e to the x. Okay, plus, now we do the other one. E to a power, right? E to something. The derivative of e to anything is itself. But then times chain rule says now you have to take derivative of what was up there. So times what? Cosine x. That's it. Number 2. Y is equal to natural log of x. This was exactly number, was it 15? Yeah, so this was natural log of s on the homework. So I changed it by making it natural log x. So the way you look at this is, here's a u. The derivative of natural log of u is 1 over u, right? So 1 over whatever was there, natural log of x, times the derivative of the u. But the u is a natural log of x, right? So what's the derivative of natural log of x? 1 over x. So 1 over x. So you could put it together and put 1 over x ln x. Okay? Number 3. Number 3 was exactly, I don't know what number it was. This one was a little tricky because of that pi x on the inside there. All right. 17? Okay. So again, pretty much this is 3 homework problems. First thing you have to do is make sure you can use L'Hopital's rule. You got to show me that. You can't just go swinging away with L'Hopital. So I'm going to take a look at this. The top goes to what? 1 minus 1 plus natural log 1. Natural log of 1 is 0. So 1 minus 1 is 0. So this whole top goes to 0. On the bottom, you get 1 plus cosine pi. What's cosine pi? Negative 1. Cosine of pi is negative 1. So 1 minus 1 is 0. So you do get 0 over 0. So you can use L'Hopital's rule. So L'Hopital says that you do what? Top and bottom separately, right? So the derivative of the top, let's see, derivative of 1 is 0. Derivative of negative x is negative 1. The derivative of natural log of x is 1 over x. So that's just what we call term-by-term differentiation, each one, because they're separated by addition and subtraction. On the bottom, the derivative of 1 is 0, and then derivative of cosine, we have to use chain rule here. So derivative of cosine of something is negative sine of that something, but then times the derivative of the something. So what's the derivative of pi x? Just pi. What's the derivative of 5x? 5. What's the derivative of 10x? 10. What's the derivative of pi x? Pi. Now we check again. I go ahead and let x go to 1. Get negative 1 plus 1 over 1 over negative sine, let's see, replacing x with 1, I get pi, and then pi again. What's sine of pi? 0. Okay, on the top, you get negative 1 plus 1. 0. 0 over 0? 0 over 0? Means what? L'Hopital again. All right, so I'm taking derivative of this red part here. Derivative of negative 1 is 0. Derivative of 1 over x is negative 1 over x squared. We've done that so many times now that I told you last class that's one of those ones you should just know. What's the derivative of the bottom there? Let's see. Yeah, look, the pi and the negative is just a number, right? That's negative pi. That's like a constant sitting out front. So I'm just going to put it out there. Negative pi is just sitting there. But then times the derivative of sine is cosine of pi x. But then chain rule says now the derivative of what was inside the sine. So what's the derivative of pi x? Pi again. And now you take the limit. So let x go to 1. You get negative 1 over 1 over negative pi times cosine of, let's see, pi times 1 is pi, and then times pi. Cosine of pi is what? Negative 1, right? Negative 1. So this piece right here is going to turn into negative 1. What's the top? Negative 1. So on the bottom we get negative pi times negative 1 times pi. Pi squared. Negative 1 over pi squared. Okay? All right. Let's get back to what I had on the board here a second ago. Today, we took our quiz, right? I'll answer questions in a second. We're going to cover 4.1 and 4.2. Next class, I want you to look at the videos for 4.3, 4.4. I want you to do the homework for 4.1, 4.2. It's right there. And then we will talk about exam 2. So I do intend next class to talk about 4.3 and 4.4, but just a little bit. I mean, I want to save at least an hour to an hour and a half of next class to talk about exam 2. All right? And then on Wednesday, we'll have the exam. So if you look at our schedule, we were supposed to have our exam on Monday. I'm pushing it back one day. All right? Questions on that? All right. Questions over homework? Anything on homework you want me to talk about? 3.7. Number 27. Yes, that looks fun. All right, so this is number 7. No, 27. Page 197. Man, I forgot I was going to give you a bonus question on that quiz. I forgot to put it on the board. Oops. It was gonna say a function f has a critical number at the value x equals c if, and then you fill in the blank. All right, let's take a look at this. This is a limit, right? So we're in the section right now on L'Hopital's rule. I'm just going to try and figure out what's happening first. What is natural log of 1? 0, right? Natural log of 1 is 0. All right, here. Let's plug in 1. That gives me pi over 2, doesn't it? Tangent of pi over 2, if you go back to tangent function, it's one of the functions you're supposed to know what it looks like, right? Here's pi over 2. What's happening as I approach pi over 2 on tangent? So, yeah, it's an asymptote. It goes like this. That's a pretty good drawing, a tangent, I might say. That's what it does. It's periodic, right? It keeps continuing this direction also. The question is, I mean, at pi over 2, it's undefined, right? On the left of it, it's infinity. On the right, it's negative infinity, correct? Which side of it are we approaching from? Right side. Why? Because the plus here means that we're going to be plugging in a number that's a little bit bigger than 1, right? And when you multiply pi over 2 by a number a little bit bigger than 1, that's a little bit bigger than pi over 2. So we're to the right of pi over 2. So where's this tangent thing headed then? When I take this limit, where is it headed? Negative infinity. Now, if you have 0 times negative infinity, is that an indeterminate form? Yes. That's something we don't know what it does, correct? What did I tell you you could do if you have this? We're trying to get to L'Hopital, but you can't use L'Hopital yet, right? Make it a fraction, right? Make it a fraction. That means you can pick one of those and drop it down. I also want to point out, in the way they wrote this down, does everyone understand that the natural log does not contain the tangent? The tangent is not in the natural log. I put the parentheses there. That's not what it means. This is a multiplication between the two. All right? I'm saying that because if it was like this, then we could actually break it into 2 logs using a property of logs that multiplication becomes addition. But because it's not, I can't use that property. So I'm going to choose now one of these, and I'm not sure, unless you want to help, which one do you want to drop to the bottom, and what's your rationale behind it? Why? Any? Yeah, if we take natural log to the bottom, let me show you both ways, okay? I'll write them side by side, and maybe that'll help you determine which one's nicer. If I drop the natural log down, don't I have to do 1 over natural log x? So I can do the derivative of the top, no problem. Derivative tangent of something, secant squared, I'm in business, right? But the derivative of the bottom, 1 over natural log x, is a quotient rule. There's no way around it. You would have to do, like this is your f and that's your g. Do y'all see that would be an issue? You could, if you wanted to, rewrite that as natural log x, all of it to the -1, and use chain rule. But either way, it's going to be kind of a pain. Now, I might wind up doing this, but my first look at this, I don't like it. Understand? So I'll put or. We could do limit x approaches 1 from the right. If I leave the natural log of x on top, and then I put 1 over tangent of pi x over 2, why is that more attractive? Because I'd still have to do quotient rule, wouldn't I? That's right. 1 over tangent is cotangent. I like that. Yes?
Why can't you at the very beginning just make tangent sine over
You could do that also. You got the wrong by doing it that way? Okay. Well, because on your derivative of the top, you had natural log x times sine of that, and you had to do product rule up there, right? Yeah, and that's maybe that's where it might have happened. I don't know. I'd have to look at it, but you could. That's okay to do. Okay, so I like this way. Let's stick with it. Limit x approaches 1 from the right. We've got natural log x over. I respect you admitting that you couldn't get it or whatever. A lot of people are too afraid to speak out like that. So we've got 1 over tangent is cotangent. Now let's do L'Hopital's rule. Now, do I have to check that this is going to be like 0 over 0 or infinity over infinity? Do I have to check it? I would like you to, but I told you already that anytime you get 0 times infinity, if you drop one of them down, you're guaranteed to have infinity over 0 over 0. It has to. Well, think of it this way. If I have something that's approaching 0 and another thing that's approaching infinity, then if I rewrite this as infinity over 1 over 0, doesn't 1 over 0 become infinite? So now you have infinity over infinity. If I do it the other way, and I leave the 0 on top and make it 1 over infinity, doesn't 1 over infinity go to 0? So now you have 0 over 0. So either way, it's going to happen. So I don't require you to show it, all right? At this step right here, I'm going straight to L'Hopital. L'Hopital. Derivative of the top. 1 over x. All right, derivative of cotangent. So what's derivative of cotangent? Negative cosecant squared of pi x over 2 times chain rule, the derivative of what was inside cotangent, pi over 2. Right? Pi over 2 is like a constant in front of x. Everyone understand that? Pi over 2x, or pi x over 2 is the same as pi over 2 times x. That's just a number in front of x, so when you take the derivative of it, you just get the pi over 2. Okay, now I'm going to have to check again to see what happens. So let's let x go to 1. We get 1 over negative cosecant squared of, see, if x is 1, that's pi over 2, and then times pi over 2. Agreed? What is cosecant of pi over 2? And if this helps you, what is secant? What is cosecant? By definition, isn't that 1 over sine? So this is the same. The bottom is just the same as 1 over sine squared pi over 2 times pi over 2. I wrote that kind of small. Can you all see that? Cosecant is 1 over sine. So cosecant squared is 1 over sine squared. And then that pi over 2 is sitting out there. So what's sine of pi over 2? 1. 1 squared, 1. 1 divided by 1, 1. Negative. So what do you get on the bottom at the end of all this? Negative 1 on the bottom, right? But then times pi over 2. Right? Wasn't there a pi over 2 out here? So you get negative pi over 2 on the bottom? Do y'all have a question on that, or do you understand? Crickets. Is that all right? And then all we have to do is flip it over, because 1 over a fraction is equivalent to the reciprocal. So the answer should be negative 2 over pi. Is that the answer in the back? Okay, good. Other question? That was a great question. Really good one. Okay, so I was hoping you all would come in with some L'Hopital questions today. 15, limit x goes to 0, x 3 to the x. That means x times 3 to the x, right? And then 3 to the x minus 1. And we're going to let x go to 0 right now. If I let x go to 0, I get 0 times 3 to the 0 over 3 to the 0 minus 1. That's the same as 0 times 1 over 1 minus 1, which is 0 over 0. Everyone understand that? Anything raised to the 0 is 1. Anything raised to the 0 is 1? What about 0 to the 0? That's different, right? 0 to the 0 is undefined. Yeah, so, okay. So can we apply L'Hopitals here? Yes. So I'm going to apply L'Hopital now. L'Hopital, yeah. Derivative of top and bottom separately. What are we going to have to do to take derivative of the top? Product rule. There's a product right there. X times 3 to the x. So derivative of a product is derivative of the first one, 1, times the second one, plus derivative of 3 to the x itself times ln 3. That comes from that thing from last class. Derivative of a to the u is a to the u natural log a times u prime. So it's times a 1 at the end, but we don't need to put it. Am I done on top? What else do I need? X. And then that's done with product rule, right? How about the bottom? Derivative, so it's two terms, right? So you can do each one separately. Derivative of 3 to the x is 3 to the x ln 3 again. But then minus the derivative of 1 is 0, so I don't need anything. So that's it right there. What now? You want x to go to 0 now? Yes? Does it work, or do we get 0 of 0 again? It works? Okay. I would plug in 0 now. I mean, that's fine, but I noticed something here real quick. I could actually factor 3 to the x out. Right, you can factor 3 to the x out of the numerator? Y'all agree? And you can cancel it. Now, it turns out I didn't need to do that because it would have worked anyway. But I'm just showing you, like, that's where my instinct took me. Like, I want to try and algebraically clean this thing up as much as possible. So I get the 1 plus x natural log 3 on top over natural log 3. Now let x go to 0, and you should just get 1 over natural log 3. But that's not the answer in the back of the book, is it? It is? It's not natural log of 1/3? It's not? Okay. Okay, good. Yes. Yes, good. I'm glad you're asking. All right, we want the limit. X goes to 0. This will be my last example out of 3.7. X goes 0 from the right of x to the square root of x. So what do we have? What's the form here? 0 to the square root of 0, but the square root of 0 is still 0. So we have something that looks like this, 0 to the 0. Is that an indeterminate form? Is that bad or not? It's a bad situation, right? Why is it bad? Who can explain to me why that's bad? It is undefined, but what's the struggle that's occurring here? Okay. Yeah, the power 0 normally wants to make everything a 1. But then 0 itself doesn't want to be 1, it wants to be 0. I pointed this out in class last time. This arrow that I draw here means in the limit. Okay? In the limit. That means the base, the x, is getting close to 0. So this is getting close to 0. This one is getting close to 0. If you go into a computer or a calculator or something, and you take 0 and raise it to the 0, it's going to say undefined, or it's going to give you an error. It's the same thing that would happen if you took 4 and divided by 0. That is not defined. We are taking a limit, though. We're saying let's get close. So the battle is like we just said. The base wants to be 0, but the exponent wants to turn it into a 1. You have to know all those indeterminate forms for the test. Right? You need to know when you can and can't apply L'Hopital's rule and things like that. Okay, so what did I say we do whenever we have an indeterminate form that involves x both in the base and the exponent? Last class. What do? Take natural log. Before that, though, you have to do something before you take natural log. Can't move that square root out yet. Hold on. Y equals. Thank you. You have to make an equation first. And the reason why you have to make an equation is because you can't do something to an expression just out of the blue. Like you can't take a number 3 and then just all of a sudden square root it. It's not 3 anymore. If you make an equation, then you can do something to both sides. So I have to make that equation first. Then I can come in with natural log on both sides. And I said last class that when you take the natural log of a limit, the natural log passes through the limit. That's the way we say that. It passes through the limit. And now you can pull the square root out. And where does that square root of x go? In front of where? In front of the ln, right? It's going to drop right here. So we've got natural log y equals limit. X goes to 0 from the right of square root of x natural log x. Now can I use L'Hopital's rule? No, because what's happening? I have this one's going to where? 0, and this one's going to where? What's natural log of 0? It's undefined, right? But as you get close to 0 from the right-hand side, it goes to negative infinity. So you've got 0 times negative infinity. And that's a problem, isn't it? But we just did a problem like that. What did we do to resolve the issue? Drop one down, right? Which one would you like to drop? Square root of x, yeah? Is that the same as dropping it down? Yes, because square root of x is x to the negative 1/2. Square root of x is x to the 1/2, and then if I drop it down, it becomes x to the negative 1/2. No questions? I don't have to check, but this one does go to a form of infinity over infinity. That's what's happening here. So I'm ready for L'Hopital. Natural log y equals by L'Hopital's rule. And I need to see this on your test, okay? You need to show me that when you're using L'Hopital's rule, right? Limit x goes to 0 from the right. Derivative of top and bottom. So derivative of top is 1 over x. Derivative of the bottom, negative 1/2 x to the negative 3/2. So natural log y equals limit x goes to 0 from the right, 1 over x. Check this out here. How about negative 1 over 2x to the 3/2? Is that the same? Why did I do that? I'm going to flip it. Yep. Let me continue this here. Natural log y equals limit x goes to 0 from the right. Let's see. I'm going to get a 2x to the 3/2 on top over the x and then the negative 1 multiplied, so negative x. Can't I reduce that power of x there? X to the 3/2 divided by x is what? X to what power? Remember, you subtract exponents. 3/2 take away 1 is 1/2. So you get x to the 1/2, don't you? And that's square root of x. And then I still had a negative, didn't I? So I'm done. I'm ready to take the limit now. So let x go to 0. And doesn't that right side go to 0? Right? To 0? So you get natural log y equals 0. Am I done? No. I have to take e to both sides, right? E of natural log of y is y, and e to the 0 is 1. The answer is 1. All right. Good stuff. So I really do like the problems like number 33, like the one we did here, because you have to go from the 0 to 0 and convert that over to the 0 times infinity, and then drop down to make it 0 over 0 over infinity, and then L'Hopital. So that kind of shows all these different skills in one problem, right? Yes. Yes. Square root of x? Yeah. From right here? Yeah, just all I did was x to the 3/2 minus 1, which gives me x to the 1/2. And then the negative in front of it was like a negative 1, so I just pop it to the top with the 2. All right, all right. Anything else out of 3-3? Out of 3-3, number 19? f of x equals x cubed plus 2x e to the x. And we're trying to find the derivative. So there's a couple of ways to do this. I actually see a product here. So I want to do a product rule right in between these two, calling this first one f and this first one g. I mean the second one g. Does that sound fair? So the derivative will be f prime. What's the derivative of f? 3x squared plus 2 times e to the x, but because there are two terms, I need to put that in parentheses, right? Plus the derivative of g, e to the x, times x cubed plus 2x. We're pretty much there. There's several ways you could do this if you want to clean it up. You can multiply the e to the x through. I'm going to wind up factoring it out at the end anyway. You can take it from both of them if you want. But you get an e to the x, 3x squared, plus 2e to the x, plus e to the x, x cubed, plus e to the x, 2x. Then take an e to the x out, put them in descending order, x cubed, plus x squared, plus 2x, plus 2. Yeah, 3x squared. Thank you. Oh, yeah. Oops, put it in the wrong place. Does that answer the question? I didn't see who asked for that. Is that all right? Okay. All right, well, I think we're ready to move on to 4.1. So chapter 4 is called Applications of Derivatives. Applications. And let me get my notes out here. All right, again, hoping you've watched the videos. I don't know if I can count on that at all, but the basic idea here in this section is that if you have a function, right, let's say that does something like that, that there's some very important points on this function that I will now plot as red dots. All these points are called local extrema, right? Local extrema. This one right here is called a local maximum. This is called a local minimum. This one's called a local maximum. And more than that, the one here on the right, this one here, is actually also called the what? Global or absolute maximum. Global or absolute maximum. So the local maximum minimum values, it's kind of like, you're king of the hill on your hill, right? That first local maximum, that dot is like the highest point around there, right? Like in San Antonio, that's like the richest person in San Antonio. That's the king of the hill, let's just say, okay? But then you go to Austin and there's someone richer in Austin. They're the king of the hill there. Understand? Then you've got whoever the richest person is in the world. They are the global absolute maximum, right? And then minimum would be like what? Just the, is there a course? Yeah, that's a good one. You're local or absolute? Absolute minimum. All right. There you go. Well, there's nowhere to go but up from there, huh? All right. Now, does this function have a global minimum? No global minimum, because there is no lowest point on this curve. So an absolute maximum is the highest point on the curve. Global minimum is the lowest point. And then all the locals just look at the neighborhood, the area around it. In all of these cases, these are called, extreme values. Now, it turns out that in this section, we come to find that if you ever have a local max or min, right? If one exists, then there's something about the tangent line there. What is it? What's the slope of the tangent line at any local max or minimum? 0, right? F prime is 0 here. Here, F prime is 0 again. Here, F prime is 0 again. So we had a theorem that was in here. It's called Fermat's theorem. It's 4.1.8. It says, if F has a local max or min at a point C and the derivative exists, then it has to be 0. Has to be. But I said to be careful. In my notes, I said be careful because it doesn't always work. You have to be careful in the order of that. And I think I gave an example in the book, or in my notes, of a function that at this point right here, the slope of the tangent line actually is 0, isn't it? But is it a local max or minimum? No. So if the derivative is 0, then local max, local min, true or false? If your derivative is 0, does that guarantee you local max, local min? No, that's false. Now, if local max, local min, and f prime exists, then I guarantee you that the derivative is 0. So if you're looking at the highest point or lowest point and the derivative exists, then it's guaranteed to be a local max or min. Can somebody tell me where I could have a local max or local min where the derivative does not exist? Give me an example of a function where I have a local max or min at some point, but the derivative is not 0. Absolute value. Correct. Good. If you have, someone else said sharp corner, right? Is that what you were saying? Yeah, if you have a corner like this, then if you look at this blue point down here at the bottom, that's obviously a local minimum, but the derivative doesn't exist because it's a corner. You could have a cusp also, something like that. Okay? Now, because local maximums and local minimums seem to occur wherever the derivative is 0 or where you have this non-existence of the derivative, we define in this section what are called the critical numbers. And what are they? That's what your quiz bonus was supposed to be. The critical numbers of a function are what? It's basically places, or you could say x values, where what? Where the derivative is 0 or the derivative does not exist. So any place on a function where the derivative is equal to 0 or the derivative does not exist is called a critical number of the function. And that brings us to the last theorem, which says that if f has local min or local max at x equals c, then c is a critical number. And that's kind of a big deal. Another way you could read that is if f has a local max or min at some value c, then the derivative is either 0 there or it doesn't exist. Right? Either your derivative is 0 or it doesn't exist. Did I go too fast? Pardon me? Well, I would challenge you the other way. Can you draw me a graph where there's a local max or min, where the derivative would be something other than 0 or doesn't exist? So can you draw something without picking up your pencil where you have local max, like a local max or local min, and you don't do this or that? See, here's a local max, here's a local max, right? In this case, the derivative has to be 0. In this case, the derivative doesn't exist. That has to happen. It's impossible for you to draw me a graph where you have this local max, highest point around, king of the hill, without having one of those two things happen. So I kind of challenge, you see what I'm saying? I mean, the challenge is that you can't do it without one of those two things happening. Now, you can do it the other way, though. I can show you an example where a derivative doesn't exist. Does not exist, okay? I can show you an example of a function where the derivative doesn't exist and it is not a local maximum or minimum. This function right here. That's the inverse tangent, or cube root. What happens is that your tangent lines on this one, as you start going here, they start to become vertical, don't they? And vertical lines have undefined slopes. So basically, you have a straight up and down. At this point here, you have a straight up and down derivative. So the derivative does not exist there. But that's clearly not a local maximum or minimum. So again, it goes back to the order of things. If it is a local max or min, guaranteed derivative 0 or doesn't exist. If the derivative doesn't exist or is 0, that doesn't tell you anything. Okay. Next thing. People like steps, right? I'm referring to 4.1.11. This is how you find the absolute max and min of a function on a closed interval. This is called the closed interval method. And what's cool about this is that we're kind of looking at a special case right now. We're saying, let's say we have a function that starts here and ends somewhere. So it doesn't keep going forever, right? It starts and stops, and it's continuous. What does continuous mean? What is draw without picking up my pencil? So if you draw a function that starts at a point, ends at another point, and it's continuous, you must absolutely have to have an absolute max and an absolute min. It has to happen. There's no way you can't. You're going to have a highest and a lowest point. It's got to happen. With the arrows? Well, the one where you were saying you were the lowest point? Tangent? That's not a continuous function. You couldn't draw it at that point. right? And it's not, see, it has to be on a closed interval. See, closed means A to B. When you look at tangent, it goes like this. The interval it's defined on here is negative pi over 2 to pi over 2, but it is an open interval, not closed brackets. Open interval means that you can keep getting closer and closer to pi over 2 without ever getting there. When you close the bracket, that means you have to actually get to that point, which means we would have to have solid dots at the end. So it's impossible to have an asymptote.
So couldn't you have 2 points go on that tangent?
Just put dots at the ends.
Well, instead of doing pi over 2, pi over 2, like do exact points. That would still be that shape of the tangent.
I'm not sure I understand. Is that what you mean? If you want me to close that interval, then the function has to be defined at that point, right? But then it can't have an asymptote, because asymptotes are places where your function's undefined and they start to explode as you get close to them, right? They start to blow up. So if you come in later and you say, okay, but define it to be this point, then your asymptote no longer occurs. And if it does still occur, if you're trying to challenge that it would, then it's not continuous anymore. Because how can you draw it without picking up your pencil now? Like if I just came in here and said, look, let me just define at the ends to be those dots. Well, now I could close off the interval, but I can't be continuous anymore because I can't draw it without picking up my pencil, right? I start up here, and I draw the next part. I have to go way down here and then come up and then come back and jump to that point. I don't know if that addressed your question or not. Okay. If you rethink it and want to talk more, we can. So the closed interval method says if you have a function that's continuous on a closed interval, then you're guaranteed to achieve the absolute max and absolute min. It has to happen. There's a method. I'll write the steps down. What about this function? Starts here, ends here, goes straight across. Does that have an absolute maximum? Let's just give it a value. How about 3? So what's the maximum value of that function? 3. So it has an absolute maximum, right? Does it have an absolute minimum? 3. The absolute max and the absolute min are the same. All right, now let's talk about the method. The method for finding these. I'm not even going to start the new page. Now, these are all written down in your notes, which I expect you to have, but I'll put them anyway. First step is to what? Find the critical numbers of f. How do you find critical numbers? What are the critical numbers? The places where what's happening? Where the derivative is 0 or where the derivative does not exist. So our first step will be to find the critical numbers. We'll have to take the derivative, we'll have to set it to equal to 0, and we'll also have to figure out where it might be undefined. And we will also evaluate f at the critical numbers. So it's kind of a two-step process here for part 1. For part 2, we evaluate f at endpoints. And then third, we compare answers from part 1 and 2. So I'll give you a second to make sure everyone has those jotted down. I really want you to understand this, like geometrically what's happening and why we do this process. Everyone got this? Moving on. No one said no. Y'all never answer me anyway, so. Okay, so let's just take an example here. I've got a function. I'm going to draw. It's going to start here. Let's say it goes up, and then it comes down, and it stops right here. Is that a continuous function on a closed interval? Yes. Does it have an absolute maximum? Yes. It's right there, right? What is happening at that absolute maximum? Tell me about the derivative there. What's the derivative? What's the slope of the tangent line? 0, right? So right here, we have 0. So that's a critical number, isn't it? That's a critical number. The critical number is where that occurs. With me? What about the absolute minimum? Does this have an absolute minimum? Yes, but it's an endpoint, isn't it? So it doesn't happen where the derivative is 0 or where the derivative doesn't exist. It happens at an endpoint. So it's possible that your absolute max or min could just occur at the endpoint. So that's why we have to check them. So part 1 of the procedure is, hey, find all the places where you might have flat tangent lines. And then find all the places where you might have any corners or cusps. Then the next part is, then look at your function at the ends and just compare all those answers. The biggest number you get out is your absolute max. The smallest is your absolute min. So we're going to find out where this thing occurs. We're going to find the x value here. We're going to find out the x values here and here at our endpoints. We plug all those x values into our function. The biggest one's the absolute max. The smallest one's the absolute min. All right, so let's go and do a problem here. The critical numbers are potential places where you could have your absolute max and min. The only way you're going to be able to tell is by taking that critical number, plugging it into the function, and figuring out what the function's spitting out. Like, if it spits out a 10 here, it spits out, let's say, a 5 here, and over here it spits out a 6. Then when you plug those in, you look at 5, 6, 10, it's easy to tell which one's the biggest, right? 10. And 10 would correspond to that x value. The 5 would be the smallest, and it would correspond to that x. Does that answer your question? Yes. Local mins and local maxes are going to come in the next few sections, okay? This is going to be on our next test. Local max, local min, I don't know yet. We'll see how things go on Monday. Holy crap, it's only 2:15. Whew. All right, here we go. All right, first problem that we're going to do here. I would like us to find the absolute max and absolute min of the function f of x equals 5 plus 54x minus 2x cubed on the interval 0, 4. Everyone have it written down? Yeah? Okay, now oh shit. Sorry. I don't think anyone caught that in time. That was all your grades. Oh man, I'm going to have to clip that out of the frickin' video. Holy shit. Damn it. Fuck. That means I have to re-render the whole project. So today's video is going to take me till tomorrow probably to put up on the web. Son of a bitch. All right. Okay, what was it? It was 5 plus 54x minus 2x cubed, right? All right, so what I want to do first, let's just look at this function. Whoa, can't even tell. It's really hard to see what this polynomial is doing. It's a crazy looking polynomial. It's a third root, or it's a cubic, right? Cubic polynomial, third degree. Let me try and change the view to make this a little better. Yeah. Let's go negative 10. 10. Inconsistent data. What the hell? I'm not sure what happened here. Let's do this. Hold on. I'm going to set center. Horizontal, 15. Let's make this 200. This is all screwed up, folks. Sorry. Let's do this. What was the interval? 0, 4? Lock this interval. Try it again. Zoom. Yeah, I think so too. I don't know if that's going to be enough for us to see this, but I'm looking between 0 and 4. Okay, do y'all see this red here? It goes way up. And what we're trying to figure out is between 0 and 4 what the highest and lowest points are, just between 0 and 4. Does that make sense? Sorry, my graph sucks so bad. It'll probably work out better in our next example. I'm still so pissed I have to redo the video. Go back to these. Okay, so the first thing you have to do, even though it's not even step 1, it's step pre-1, okay? You have to check to make sure you're looking at what? This function has to be what? Continuous. Is this a continuous function? Yes. Why? Why? Just because? A little more than vertical line test. You have to go back and look at the the section on continuous functions. All polynomial functions are continuous. All polynomial functions can be drawn without picking up your pencil. So this is continuous because it's a polynomial. Okay, do we have a closed interval? Yes. Okay, so you are allowed to use this theorem. I never gave you the name of it. We just call this the closed interval method. But those are the conditions we need. We have to have continuous function closed interval. Now, first step. I need to figure out where the critical numbers are. So to find out my critical numbers, what I'm going to do is I'm going to take the derivative first. So what is the derivative of f? 54 minus 6x squared. Is everyone with me? Yeah? I don't know why I keep asking. Why do I keep on asking y'all stuff? Right? I'll show you what graduate school was like for me, just so you realize. I find a lot of value in trying to ask my students if they have questions. This is what graduate school was like to me. Okay. We used to joke around about it too. Our professor would get up there, come up with his lecture, and would start writing, right? And it seemed like he was just doing this. That's what it seemed like. But you're just sitting there just copying down everything he's doing. And never turned around, ever, whole semester. Never turned around. Never said, any questions? Talking to the board. How many people were in your class? I think 6. In that class, 6. Yeah. Yep. But here was the thing, though. At that point, those are the best notes that I ever had. Okay? He was sharing his interpretation of that subject with us. So I had to, decipher it and make it make sense and read it and understand it. But he wasn't there to explain it. He was just there to share his view of it. So I guess what I'm saying is just, I ask you if you have any questions because I really want you to stop me if you do, but I mean, you don't stop me, all right? Then it becomes more like I'm just writing and talking to myself here, but. Can I proceed? Okay, what am I going to do? I'm going to look at two things. I want to know when the derivative is 0. This is a question I'm asking myself. Where is that derivative 0? And then the other question I'm asking myself is where does this derivative not exist? So let's do these one at a time. First one, when is it 0? Well, just set it equal to 0. This is a quadratic equation. There's several ways to solve it. I'm going to solve it the easiest way that I think, which would be to move the 6x squared over to the other side to make it positive. Divide both sides by 6. What's 54 divided by 6? 9? 8? What? 9? Okay, 9 is x squared. And now I'm going to take the square root on both sides. Anytime you take the square root on both sides of an equation, you must do plus or minus, right? Because there are two numbers that you square to get 9, right? 3 and negative 3. So you have two answers there. So there are two potential places where I might, maybe, possibly have the absolute max and min. It's when x is 3 or negative 3, maybe. Now, what about the derivative not existing? Look at the derivative, and when we say, where does the derivative not exist, I'm saying, where is the derivative undefined? Well, look at the derivative. What type of function is the derivative? It's quadratic, right? It's polynomial. Isn't a polynomial well-defined everywhere? So NA is what I'm going to put to stand for like not applicable. Basically, there is no place where this happens. More mathematically speaking, we would say empty set, right? That's saying there's nowhere where the derivative is undefined. I'm done with step 1. I have found the critical numbers. Well, no, I'm not done with step 1. I found the critical numbers. Now what do I need to do, according to my notes here? Evaluate the function at the critical numbers. So I'm going to go to the original function, f. I'm going to plug in 3, and then I'm going to plug in negative 3 into the function. Not into the derivative, right? Into the original function. So when I plug in 3, what do I get? I'm plugging it into that 5 plus 54 times 3 minus 2 times 3 cubed, which equals some number between negative infinity and infinity. Anybody get 113? Yes? Yeah? Did you have that already? Yeah? Okay. And then negative 3? What do you get? Negative 100, 103? That sound good? Anyone else get that? Anyone else get that? That's what I'm going to bring that up. Hold on. Did anyone else get that? Negative 1? Okay. So now, when you looked at these numbers, these two critical numbers, right? What that's saying is that, look, if I just go out and look at this graph, right, and I go out to 3, my function's way up at 113, right? And if I go out to negative 3, it's way down here at negative 103, something like that. But where are we looking? We're only looking between 0 and 4. So we're supposed to be focusing all of our attention over here, between 0 and 4. Right in there. So what can you tell me about the value of the function negative 3? It's not relevant, right? It's not relevant to the problem. So that when I found the two critical numbers, positive and negative 3 here, I should chunk any of the numbers that aren't in the interval. Now, the worst that's going to happen is that you're going to evaluate it and waste a little bit of time, but you don't want to count that as a possible answer. So this one right here, we should just scratch from our thoughts. That's a common mistake, all right? You get the critical numbers, then you forget the interval. So I'll put a little note under there, not in 0, 4. Okay, now we're done with the first step. Now step 2 says to do what? Whoa, uh-oh. Evaluate function at endpoints. So what are the two endpoints of the interval? 0 and 4, right? Now 0 should be easy because this is a polynomial. At 0 you get 5. And at 4 you get, anyone do 4 yet? 93? So step 3, you want to compare. So I'm going to go and look at step 1. I had f of 3 was 113. Step 2, I had f of 0 was 5. And f of 4 was 93. And just look at the biggest number you have, right? Biggest number would be 113. This is your absolute max. Smallest number you have is 5. That's your absolute min. So we're referencing the output, right? What came out of the function, the biggest one and the smallest one. Now, it's one thing to tell me what the absolute maximum is and what the absolute minimum is. I prefer for you to be able to tell me what the absolute max and min are as a point. In other words, 3, 113, and 0, 5. This to me is what I would like to see on a test or quiz. Of course, tell me it's absolute max, absolute min, but there's more information than you just telling me 113 is absolute max and 5 is the absolute min, because by showing it to me as a point, that also tells me where it occurs, right? Like what x value.
So if we left it like that, we didn't put a point, we like a point off.
I wouldn't take off for it, but it's still right. That is the absolute max, but written as a point is preferred. All right. Let's do another, and then we'll take a break. All right. No, that one's too easy. Let's look at f of x equals x minus natural log x on the interval 1/2, 2. What's the first thing I'm going to check for? Is it continuous? Natural log is not a continuous function, because remember what natural log does, right? It dives down. It's not defined for negatives. But look at our interval. It's from where? 1/2 to 2, right? Is natural log continuous there? Yes. So this is a continuous function on that interval. And our interval is closed. So I'm checking that. Now, step 1. I'm going to need the derivative, right? So critical numbers. Let's talk about the derivative here. It's what? 1 minus 1 over x, right? 1 minus 1 over x. And then from there, I want to know two things. Where's the derivative 0? And where does the derivative not exist? Let's talk about derivative being 0. Take your derivative, set it to 0. How would you like to solve that? You can almost just solve it by looking, but... Okay, take negative 1 over x to the other side. It becomes a positive 1 over x. Then you can multiply both sides by x. X equals 1. Is 1 in that interval? So I'm going to put a little check here. That is in 1/2, 2, isn't it? So I have a good critical number. I might have a max or min there. All right. Does the derivative ever not exist? What if I plug in 0 right there for x? If I plug in 0, it doesn't exist, right? But what can you tell me about x equals 0? Yeah, but that's not in 1/2, 2. So I'm not even going to consider it. So then I'm ready for the next step. Endpoints. What's f of 1/2? what's f of 2? So we're plugging these into the original function, right? Oh, wait, I forgot it again. What did I forget on step 1? Damn it. Yeah, I was supposed to take my critical number and plug it in. Go back up to step 1. Right underneath here, I was supposed to find f of 1. Right, plugging it into the function. So we plug it in, we get 1 minus natural log 1. Natural log 1 is 0, so we get 1. I find it hard to believe that we're barely halfway through today. Doesn't it seem longer to you? It's dragging today. All right, then I plug in 1/2. Did I lose anyone there, or is everyone okay with what I did here? Is that right? And I plug in 2. Now, because this is the natural log function, it might be impossible for you to figure out what these numbers are. So this is where you get your calculator out and do, 1/2 minus natural log of 1/2 and get it as a decimal. I'm getting 1.193, and then 2 minus natural log 2. I'm getting 1.307. Is that all right? Step 3 is to figure out your absolute max and min. So compare them. And we can do the comparison now because they're all on the page. Where's the absolute max? Or what is it? 1.3? This is my max. My min is what? 1? Agreed? So when I compare, I have a maximum. It actually occurs at the point, 2 is what I plug in. What do I get out? 1.307? You could either put 1.307, that's an approximation, or you can do 2 and then 2 minus natural log 2. The one on the right is known as the exact answer. The one on the left is the approximate. Your minimum occurs at 1, 1, doesn't it? You plug in 1, you get 1 out. Just remember that it's the y value that's the max or min. I just put it as an order pair so you can tell where it happens. See if I can get this piece of junk to work again. So is x minus natural log x? Here's that function. All right, there it is. But I was only looking at it between 1/2 and 2. So I was focusing all my attention. Why is it not drawn? Oh, did I mess this up? 1/2 and 2. Changed, huh? So only looking right there. You can see that the lowest point on this graph happens somewhere around here, right? Well, we can tell you exactly where, right? It happens when x is 1, and what does it spit out? 1. Does everyone understand graphically what I'm doing or what we've done? We've taken a function and been able to identify that point. It's going to be big. There. That's the 0.11. So, all right, y'all look spent. Let's take, 10 minutes? Is that what we usually do? 250? 255. We'll make it 255. We'll give you an extra little break. Come back and do a couple more of these.